Curves in industrial design. Effect of the basis functions on the curve. Any B-spline curve of degree n composed of S Bezier pieces can be written as a linear combination of the B-spline basis functions n sub 0 n to n sub m n with coefficients d sub 0 to d sub m, which are the points of the control polygon of the curve. The parameter t runs over the time interval u sub 0 to u sub s. The number of vertices depends on the degree of the curve and the number of its Bezier pieces. Precisely, if there are m plus 1 vertices, m plus 1 is equal to s, the number of Bezier pieces, plus n, the degree of the curve. Hence, for quadratic curves, the case n equals 2, there are s plus 2 vertices. And for cubic curves, the case n equals 3, there are s plus 3 vertices. The B-spline is said to be uniform if each Bezier piece is traversed in the same amount of time, here denoted h. In this case, the kth piece corresponds to t running from u sub k minus 1 to u sub k minus 1 plus h. The B-spline curve is contained in the convex hull of its control polygon. Every point on the curve is a barycentric combination of the vertices of the control polygon. In the picture, P is the point on the curve at time t sub 0. It's expressed as a barycentric linear combination of the control points. Here we see that 3 of the coefficients are 0, those corresponding to the control points d sub 0, d sub 4, d sub 5, while the coefficients of d sub 1, d sub 2, and d sub 3 are non-zero. That the coefficient of d sub 2 is the biggest means that d sub 2 influences the position of p the most. That the coefficients of d sub 1 and d sub 3 are positive, but smaller than that of d sub 2, means that they do influence the position of p, but less so than does d sub 2. That the coefficients of d sub 0, d sub 4, and d sub 5 are 0 means that these control points don't influence the position of the point p. Here we see the B-spline at time t equals 0. As we slide t along the bar above, p moves along the curve. The control points indicated in orange and red are those which influence the position of the point p at the indicated time. The control point indicated in red, in this case t1, is that which most influences the position of p. Those indicated in orange are those which influence the position of p, and those indicated in blue are those which do not influence the position of p. So we see that as we move d sub 1, p moves. If we move d sub 2 or d sub 3, p moves, but less so. If we move d sub 4 or d sub 5, the curve distorts, but p doesn't move. As we change the time, p moves along the curve, and the control points which affect its position change as well. We see that as we've increased t, d0 has ceased to influence its position, and now d sub 4 does influence its position. If we look at the right, what is indicated are the graphs of the basis functions that influence the position of t. What we see, for instance, in the current moment, is that the control points d0 and d5 don't affect the position of p. This corresponds to the fact that t is not contained in the interval on which the graphs of these basis functions are positive. As we change t, and it moves outside of the interval on which basis function n13 is positive, the corresponding control point, d sub 1, ceases to influence the position of p. For a cubic B-spline curve, at each time t, there are at most 4 non-zero basis functions. That is, each point of the cubic curve is given in terms of at most 4 consecutive vertices from the control polygon. For instance, in the curve depicted here, only the control vertices d1 to d sub 4 affect the position of p, and only the corresponding basis functions n sub 1,3 to n sub 4,3 are non-zero. In general, if p is a point on a B-spline curve of degree n, The basis function n sub kn at time t0 can be understood at the rate at which the coefficient d sub k affects the position of the point P. There are at most n plus 1 non-zero basis functions, and they are necessarily consecutive. The position of P depends only on the positions of the vertices of the control polygon whose corresponding basis function is positive. Therefore, the vertices of the control polygon control the curve locally. Moving a vertex of the control polygon affects only a segment of the curve close to that vertex, but it does not affect the whole curve. When we move the vertex d sub 3, the curve deforms locally, only in a region influenced by the nearby vertices, and it's unchanged far away. If the B-spline curve has degree 3, the curve is contained in the union of the convex hulls of each set of 4 consecutive vertices. Here we see the convex hull of the first 4 vertices. Here we see the convex hull of the next 4 vertices, and so forth. We see that the union of these convex hulls contains the curve. However, it's important to note that the convex hull of all the vertices of the curve can be larger than the union of the convex hulls of each 4 consecutive vertices.